Hello and welcome to 5.3, the Fundamental Theorem of Calculus. This is obviously a very fundamental theorem in the study of calculus, and it is what lets us find integrals using antiderivatives. So the first part of the Fundamental Theorem of Calculus says that if f is continuous on a closed interval a to b, then the function defined by g of x equals the integral from some number a up to x of f of t dt, where x is between a number a and a number b, is continuous on that closed interval a to b and differentiable on the open interval a to b, and g prime of x is equal to f of x. So in other words, this is saying if you take the derivative of an integral, you get back the inside stuff, as long as that integral starts from some number a and is evaluated up to x. Okay? So in other words, okay, if big F of x is equal to the integral from a to x of f of t dt, then f prime of x is equal to the derivative of the integral from a to x of f of t dt. This is equal to f of x. Okay. Therefore, big F prime is equal to little f. And if we think about it, the antiderivative of little f was big F. So the derivative of big F would be little f. Okay. If you take the integral of the derivative, you get the original function. Integrals and derivatives are inverse functions. The second part says that if f is continuous on a closed interval a to b, and big F is any antiderivative of little f on that interval a to b, then the integral from a to b of little f is equal to big F of b minus big F of a. In other words, the integral from a to b of some function is equal to the antiderivative of that function evaluated at the upper limit minus the antiderivative of that function evaluated at the lower limit. Okay. If little f is is larger than 0 on that interval a to b, then the integral is the area under the curve between a and b. Okay, so in other words, if the function is completely above the x-axis, then when you do the integral using the antiderivative method, you are also going to get the area under the curve. There's also another little bit that lets you move this big F of a over so that you have big F of a plus the integral from a to b of little f is equal to big F of b. So you're just moving this big F of a over to the left. This basically tells us the initial amount, which would be big F of a at the lower bound, plus this integral is equal to the current amount, assuming that b is our current amount. And this is usually used in rate of change questions where you have time as your upper and lower bound. So you usually have like a T1 on the bottom and a T2 at the top. And usually you're doing like a rate in minus a rate out. So if we think about this, your derivative is usually a rate of change, right? So if you think of little f as the derivative of big F, then your derivative is usually a rate of change, right? So if you integrate that rate of change, you're undoing that rate part. So let's say my rate of change was meters per second. If I integrate that rate of change, the units I will have left would be meters, okay? Because I'm undoing the derivative. It's like I'm going from velocity, undoing the derivative and getting back to my position function, for example, okay? And that could be any rate, not necessarily velocity or meters per second, but that's just an example. All right, let's try some questions. So I want to find the area under the curve of f of x is equal to 4 minus x on the interval 1 to 4. So I was just told that if the function is greater than 0 on our interval, then taking the integral using the antiderivative method is the same as using the rectangle method we saw last couple lessons ago. So my function 4 minus x would look something like this. This is 4, this is 4, this is 0, this is y equals 4 minus x. Okay. Now, if x is 1 and 4, that means that my area would be here. Okay. And this function is entirely above 0 between 1 to 4. So that means that my area under the curve is equal to the integral from 1 to 4 of f of x with respect to x. So this would be the integral from 1 to 4 of 4 minus x with respect to x, which we were told is big F of b minus big F of a, big F meaning our antiderivative. My antiderivative of this would be 4x minus x squared over 2, or 1/2 x squared, plus c. And we would be evaluating this from 1 to 4. So this is what the notation looks like. Often you'll include a round bracket to the left. Sometimes you'll put the whole thing in round brackets. But this notation at the end says we're going to evaluate from 1 and end at 4. Now, remember, once we plug these in, what's going to happen is I'm going to do the 4 first. So I'm going to have 4 times 4 minus 1/2 times 4 squared plus c minus 4 times 1 minus 1/2 times 1 squared plus c. And you'll notice that we end up with a c minus c here, and those c's cancel out. So when we do a definite integral, this will always happen where this c will cancel out when you evaluate. So we don't actually need to include the constant here on definite integrals only. Okay? So only if you're actually evaluating. So this is going to give us 16 minus 8 minus 4 plus 1/2, or 4.5. And I could have also just found the area of the triangle. Area of triangle is half base times height, which give us half. My base is 3, my height is 4, which, sorry, my height is not 4, my height is 3. I'm not evaluating. My height should be 3. Because this point here would be 4 minus 1, okay, which gives us 4.5. So I could have also just found my area using geometry if I drew this curve, but sometimes they're going to be a lot more difficult than triangles and rectangles. All right, next one. We are being asked to just evaluate this integral. So again, our integral is evaluated as, this should be f of 0 minus f of -2. Now, before we do this, I would change this to be the integral of -2 to 0 of x plus x cubed by distributing this x into the brackets of dx. This is a lot easier to find the antiderivative of than something that is a product. This is going to give me 1/2 x squared plus 1/4 x to the 4th. I don't need my plus c because I'm evaluating a definite integral. And I'm evaluating this from -2 to 0. F of 0 is going to be 1/2 times 0 squared plus 1/4 times 0 to the 4th. F of -2 is going to be 1/2 times -2 squared plus 1/4 times -2 to the 4th. This first thing, I just get 0. So I get -1/2 or minus 1/4 times 16, which gives me -2 minus 4, which gives me -6. We'll try another one. This one, again, I would rewrite before you do the antiderivative. I would rewrite this as x to the -2 dx. The antiderivative of this would be x to the -1, but then I would need a negative in front. Now, the problem is that we have to look at continuity here. remember that we said we could only do the integral way back at the beginning if f was continuous on a to b. If I look at this, is f continuous? No. This is not continuous on -1 to 3 because 1 over x squared does not exist when x is equal to 0. Therefore, the integral of -1 to 3 of 1 over x squared dx does not exist. So even though we can find the antiderivative, and I can plug those things in, I shouldn't be evaluating this because it's not continuous. And if I think about what this thing looks like, I would have an asymptote, okay? And what's going to happen is I'm going to have portions of my curve that go up towards infinity or down towards negative infinity. So I have an infinite area that's contained, so I can't actually evaluate this. So the next one we're going to look at, we need to keep this in mind. This is the last one. So I'm evaluating from 1 to 4 f of x, this piecewise function. And notice how this piecewise function switches when x is 3. That is contained in my interval. I'm going from 1 to 4. The question is f of x continuous? And the point of contention would be when x is equal to 3. So f of 3 from the right-hand side would be f of x, right, which is just 3. F of 3 from the left-hand side is just going to equal 3 because f of x equals 3 if x is less than 3. So yes, we are continuous, we can continue. Now, when we do the derivative of a piecewise function, we're going to break it into the two pieces. We're going to go from 1 to 4, but we're on a different piece in different portions of this integral. From 1 to 3, our f of x is different than when we are going from 3 to 4. From 1 to 3, we are less than 3. Our function is just 3. But 3 to 4, we are bigger than 3. Our function is x. This means my antiderivative of the first function is 3x. I don't need the plus c because I'm evaluating from 1 to 3. My second function, my antiderivative is 1/2 x squared. I'm evaluating from 3 to 4. So this is going to give me 3 times 3 minus 3 times 1. And this is going to give me 1/2 times 4 squared minus 1/2 times 3 squared, which is going to give me 9 minus 3 plus 16 over 2 minus 9 over 2, which is going to give me 6 plus 8 minus 4.5, or 9.5. So the first thing is always check your continuity. You're not going to need to do that if you're integrating a polynomial, but anytime you have a rational, a piecewise function, check your continuity before you begin. If you are not continuous on your interval at which you are trying to evaluate the integral, then you need to stop. That integral does not exist. If you are continuous, you may proceed. Okay? The next thing you need to check for a piecewise function is if you are switching pieces somewhere in that interval, you need to write your integral as two separate pieces, one for each piece of the piecewise function, and your bounds will be whatever section of your piecewise function you're in. So for us, we went from 1 to 3 on the portion where f of x equals 3 because our function said if x was less than or equal to 3, f of x was 3. We then had from 3 to 4, f of x was equal to x, and that's because in our function, it says if x is greater than 3, f of x equals x. And that is it for this section.